So I'm going to spend a little bit of time introducing 1010 data because I'm going to guess nobody's ever heard of 1010 data in this room. Raise your hand if you've ever heard of us. 1, 2, wow. Wow. That is way more than ever. Like usually I get like 1 person, maybe 2. So there's like 6 or 7 of them. Tell me about it. All right, so I'm going to explain a little bit about who we are, what we do, and a little bit of history about how we got to do what we do. And then I'm going to jump into a couple of three different examples. I'll try to describe the business case that goes along with them, and then jump into a little bit of code with some of the examples that I talked about. If I see everybody cringing as I describe the code, I'll stop and move on. If I see everybody perking up and getting excited about the code, then cool, we'll talk more about code and less about the business cases. So perfectly happy jumping back and forth between them. So who's 1010 Data? We've been around for 13 years. That's a long time for only 5 people in the room to have heard about us. But we've been sort of playing stealth. We've been in the financial industry for the majority of that time. Over the last 4 years or so, 3.5, 4 years, we've sort of crawled out of that stealth mode of operation. Where our roots are the financial industry and trying to process ridiculous amounts of data. And I'm not saying big data, I'm just saying ridiculously big data. But, and I'll make the case about that in a minute. And so we take on these really, really large data sets. We process through them very, very fast. We claim that we're the fastest, but so does everybody else. So unless you actually see it, you're not going to believe it. So if you're interested afterwards, I can definitely show you, but we'll talk about that separately. We are a platform in the cloud, meaning that you will give me your data, and I'll put it up, and you analyze it on your own. So that's sort of the definition of what we do and how we do it. Over the last 9 years or so, we've been profitable. We are self-funded, and we are about 110 people at this point. And we are hiring, so if you get excited by any of the stuff that I talk about, let me know. All the technology that we have is proprietary. We wrote everything from scratch. So everything that everything I'm going to say and every claim that I'm going to make, it's all based on the stuff that we built from scratch, every line of code. So I said ridiculously large amounts of data, and I'm going to focus on this notion of rows of data rather than terabytes or petabytes. If anybody's dying to know how many petabytes that is, come to me afterwards or ask me a question. I'll try to answer it. But in the meantime, to me, as a modeler, which is sort of where I grew up and the kinds of things that I did, as a modeler, it's more important and more interesting to me to try to observe, collect observations about some real-world event. So to me, rows of data are substantially more interesting than how many terabytes it represents. So we manage, on behalf of our clients, some 14 trillion rows of data. That's raw data they deliver to us. And then we do stuff with it, and maybe there's an extra copy here and there for whatever reason. But we try to not to have extra copies. I'm going to go back to that notion a couple of times. It really matters. You really want to have 1 copy if you can help it. Hang on to that, because I'm going to come back to it. We have some really interesting data. You were talking about econometrics. I have every mortgage, every retail transaction, real estate transaction ever on our platform. And people on Wall Street analyze that. And if you're thinking about what that represents, that's 6 billion rows of data in one place. So one table, 6 billion rows of data, and you want to ask a question. What is the relationship between interest rate fluctuations and prepayment rates of mortgages? I'm looking at you because you're the economist. But that's sort of the kind of thing that we try to answer for our clients, or we could just give the platform over to them and they can do whatever it is they want. A lot of times they actually don't want us to know what they're up little hedge fund someplace, you have some trick up your sleeve, you don't want us to know, fine. We don't need to know. So you'll run your query inside of some code that you compiled and you put up and you ran. We don't know anything about what you did. All we know is that you sucked some data out. So that happens there. The other thing that we look at the world with is this lens of time series. So everything that happens in the world happens in time. So we're going to take a record of that event in time and store it in the database. So again, at our root, we're a database. So we got to be ridiculously fast to be able to do all the stuff I'm going to make claims about in a minute. So typically what happens out there with the majority of the folks that you're going to talk to is that they're building some sort of a stack, and somewhere along the stack people are going to fit in. So either you're a database vendor, or you're a cube guy, or you're building some sort of analytical platform, or you're a visualization guy, or you're an ETL guy. Somewhere along the line, you're in that food chain. We sort of dispense with that. We don't think that there is a need for a stack. If you have a single copy of the data, and if you can actually operate everything you want to do, you want to build your econometric models, fine, do it in the database. You want to do some reporting, some aggregation, some analysis, whatever it is you do with a cube, and you want to visualize this stuff, you should be able to do it on that single copy of the data. And you should be able to do it all in one place. In place in the database. All fine. So that's us, and that's the end of my advertisement. So we basically live everywhere from the dashboard to descriptive analytics to predictive analytics. We haven't really done much over here. So for those of you who are sort of into automated data mining, we haven't really done enough there yet. We're playing with some ideas. We haven't gotten there yet. I actually have a soft spot in my heart for this. I just haven't had time to do anything with it yet. But to us, really, that whole thing should sit on top of a single copy of the data. And if you can afford that, and if you can figure out how to do that, then we should at least compete. Or maybe cooperate. So I said ridiculously large data sets. That's how many rows in a single table. If you know of any other database that outright can do that on about 10 servers bought from Dell, then I want to talk to you. So if you buy them from Dell for about $15,000, $20,000 a pop, and you can do that many rows in it on 10 servers, let me know. Come by afterwards, hang around, we should definitely talk. All right. Let's jump into code. So to be able to analyze the data that I was just talking about, you got to be, so the one that I was just showing is a consolidated quotes. This is, there's another piece to this puzzle, which is every trade that has ever occurred since 2003 all the way to the present, loaded onto 1010 on a daily basis from the New York Stock Exchange. So imagine every single trade that has occurred. So the trades, the quotes are much larger. They're about an order of magnitude, a little bit more than an order of magnitude now, larger. But the trades themselves are about 57 billion rows of data in one place. So one table, and you're trying to run a query on it. For those of you who are into writing queries, you'll notice that the query language that I'm showing you here is very different from the one that, from pretty much anything you're used to, unless you're into 1010 data. What we're doing here is we're basically generating this visualization. There's specification for the visualization itself, which is what the graph spec is giving you. And that's laying out the background again. And this is the actual query that is going to run through the 57 billion rows and generate a candlestick chart. So what exactly is happening? We're selecting a start and an end date. we're choosing a particular symbol. In this case, it's Google. We are generating the candlestick data, which is the high, low, the average, the weighted average, the first and last trade of the day. So for that period of time, we're actually looking at all of that getting generated. So that's a pretty straightforward thing, and the ratio that you're seeing here, which is the actual query being a few lines, roughly about the same number of lines for the visualization part of it, is a little bit misleading. Think about what you normally do with visualization. Somebody else takes care of that problem. You write the query, you write the stored procedure that does whatever it is that it's supposed to do, and then somebody else writes the visualization for whatever it is that needs to be visualized. The language is basically capable of taking on the entire task. Again, think about a single copy of the data, so I want to be able to do every operation inside of that, on top of that single copy. So this is one of the pieces of the puzzle. I want to be able to do visualization directly inside the database. So hang on to that. I'm going to come back to that in a little bit, but I want to switch gears to talk about a little bit of the sort of the predictive modeling piece of the conversation, which should be the focus. I won't make you read all of that. How many people actually build models in the room? Okay, a good number of you. So you guys take a nap. It'll be about 3 minutes, and then you can wake up again. If you remember from high school math, where they made you run a regression, what you were doing is basically you had an x-axis and a y-axis, you have a cloud of dots, and you're sticking a line through it. And that line is basically your model. If you're brilliant and really, really lucky, you'll end up with f is equal to ma. You know, something elegant, gorgeous, and beautiful. That's sort of the happy place of every modeler, that you find something that fundamental and beautiful in the data that you're looking at. Doesn't always happen. Hasn't happened to me yet, but one of these days I'm hoping. The process that we go through to get to that beautiful place is usually to take, we sort of describe what we think is going on in the data, we do some descriptive analytics, we sample the data, we then pull that sample, we verify that our sample is good, we're very religious about that, we want to make sure that the sample is done correctly, we spend a ton of time doing that, we pull the data and we do a bunch of pre-processing, we transform the data, so that we massage it, like my buddy used to say, until it confesses. And then when it confesses and it's ready, we shove it into some algorithm, logit, probit, whatever the algorithm is that you have, and that algorithm is going to tell you what the relationships are, hoping that collinearity is not an issue, and hoping that all sorts of bizarre statistical properties in the data is not going to, you know, pop out and sort of destroy the model that you're trying to build. And then you realize that you made a mistake in that process. There's a lot of detail that you have to keep track of. And you do that, and you find that you screwed up. I've done that. And then you come back to the beginning, and you say, well, my sample wasn't really a good sample. And I'm going to go back, and I'm going to try to do the sample a little bit better. Maybe that was the problem. Maybe the algorithm that I chose wasn't really the right one. Maybe the assumption about the distribution of the variables that I took in wasn't really the correct one, and so on and so forth. Wouldn't it be great if you didn't have to sample? That would just like sort of dispense with that silliness if we can. That would be awesome if I could just get rid of that one. It's a lot of processing power, and it's really, really expensive. So if you have to do sampling, you're spending a tremendous amount of time verifying that your sample works and everything holds together properly. So if you could get rid of that, that would be a brilliant thing. You do your model testing, you do, you know, sort of revisit the problem over and over again until you settle into a set of models that you're happy with. So I'm going to pick on you again. In the world of econometrics, one of the things that people do in mortgage-backed securities is they build models for mortgages, for the different class of mortgages that are out there, and believe it or not, except for you, how many people know how many mortgages there are, how many types of mortgages there are in the US? Take a guess. If you're within an order of magnitude, you get an extra slice of pizza. All right, 1,600 different types, and increasing. Every single day, there's another type of mortgage that's getting rolled out. So you got 1,600 different types of mortgages, and you're trying to build a model. Build a model that predicts when the mortgage is going to pay off. That payoff is really, really important because it means cash flow. So if you're an investor in that thing, and you know that the guy is going to pay their mortgage off in a month, 6 months, 9 months, then you want to know because it matters to your cash flow. And one of the examples I'm going to jump into is about that. So if you have to build 1,600 models, it's going to take an insane amount of time. Because each of these models are different, separate. All the stuff that I was talking about, this whole methodology that I cut and pasted off of the web, this whole methodology is going to be the thing that you're going to have to care about for every single one of those guys. 1,600 models. So it's no surprise that a typical group of prepayment models require a staff of 10, 15 people with about a year or two worth of lead time to start from scratch. So a typical firm on Wall Street spends that kind of effort and time into having a prepayment set of models for the prepayment risk. And the majority of that time, by the way, is spent on the estimation. Because the CPU time is insane. You're talking about, insane amounts of time that you have to spend on that. And if you made a mistake, you get fired. Wall Street has no compassion for people making mistakes in that area. When I was at GMAC Mortgage, when I was working there, that's what happened. We had a separate team that was doing prepayment modeling. They screwed up, came up with the wrong projection. Company lost tens of millions of dollars that month, and that whole team, wholesale, fired. Because they screwed up. So it's very expensive. And the classical approach is very, very expensive in doing this kind of estimation. And there's a whole lot of different assumptions that are built into the process. You're catering to the middle of the distribution. You're assuming something about the distribution of data coming in, and that's how you're building your models. This is, again, classically correct. And however, if you go back to that idea that I was describing at the beginning, where I said there's a cloud of dots, you have an x-axis and a y-axis, and you stick a line through it. Well, imagine half of those guys in there are female, and half of those guys in there are males. And if you knew that about the data, dimensionality for those of you who are modelers, if you knew that about the data, you'd say, well, maybe I should have a separate line for females and a separate line for males. And then you'll say, well, but I also know that their age buckets are different. Stage of life is different. So I'll take the guys, old fogies like me, whose first kid is through college and the second one is about to go to college. That guy is different from the guy who just graduated from college. So I'm very different from my older son. So maybe we should have two different models for me and my son to try to predict whatever behavior you're trying to predict. So now you're separating the two of us, and each of these lines that you're generating through the cloud has a slightly different slope to it. Because each of them is basically behaving differently. The modelers in the room are all sort of nodding because they know exactly what I'm talking about. Because what you're doing is you're trying to sort of figure out how to predict what's going to happen next. Now, I'm talking about it in 2 dimensions, imagine it in n dimensions, and n being very, very long. Sampling that kind of a space can create all sorts of problems. This guy knows about it a little too well. This is a very famous case where sampling sort of got the best of it. Let's jump right into what that means for a classical problem. I I'm willing to bet that almost everybody in the room has bought something from Amazon at some point. And when you buy something from Amazon, what Amazon does is they come back to you and they say, people who bought this book also bought these other books. In retail, that's referred to as an affinity measure. So the affinity of these two SKUs, these two products with each other is very, very high. So what they have done is basically looked at a very simple affinity relationship, which is basically looking at the number of people that bought the stuff together versus the total population, which is the denominator. You look at those three probabilities, and boom, you have an affinity measure. Very simple mathematical thing to do. It doesn't really predict whether or not you're going to buy that thing. There is a high likelihood that you may buy that thing. And if you have an enormous population of people buying stuff from you, you get close, because that probability is driving it. Wouldn't it be great if we took that idea one step further? We took advantage of that piece of the puzzle, meaning the affinity, but then we started to look at the behavior that each person exhibits. If you go to your favorite grocery store, when you walk in, they ask you if you have your loyalty card. If you pass your loyalty card through, the data is being collected of all the transactions that you've ever had. If you're using your credit card and not your loyalty, well, rest assured, they're matching it on the credit card. All the transactions on that credit card go back in history. In effect, you have a loyalty card if you're using a credit card. So now I know every single thing you have ever bought in your transactions with that store. I live in a neighborhood, I've been there for 14 years. For the last 14 years, pretty much all the time buying my stuff from the same place. Yeah, I go to Costco every once in a while, and I go to somewhere else to buy some other stuff. But most of the time at this one grocery store, use my credit card or my loyalty card, they know me. Yet, when they go and build a model to try to predict what I'm going to buy, they look at the affinity of beer and diapers. I don't care about diapers anymore. My kids are grown. So if it doesn't matter that that affinity exists, it doesn't apply to me. Even if it's true that that affinity exists, which by the way isn't true. But even if it was true, it doesn't apply to me. It's irrelevant. So why is it that they're still sending me that kind of advertising? Costco sends you an advertising, which is everybody in the country gets the exact same booklet of coupons. And out of the last 5 years of having purchased stuff at Costco, I can tell you that maybe 2 or 3 of those coupons were actually useful. They're spending a ridiculous amount of money to try to catch me. It's silly. If they built their models on me, not on my cohort, not on the group of people that I belong to, not to my demographic, not to the place that I live in, which is, by the way, all the different ways that people build models. So male, female, age, those are the examples I was using earlier. And you look at my demographic, other demographic attributes that I have. In 2008 and 2007, it became very apparent that people buy beyond their means when it comes to real estate because they're speculating. So the guy that went and bought a house 3 times what he should have, that guy is now living in a geographic area which suggests a different demographic than his financial wherewithal. So selling him the same product that you sell his neighbor who got there because they have a ridiculous amount of money and that's how they got there is silly. You got to know him separate from his neighbor. You got to build him a model that is independent of everybody else, assuming you have enough observations. So go back to the original thing that I was saying. We collect events in time and put them into a database. These are rows of observations. That's what we do. So if I have enough observations about you, if I know that you have been there for 14 years and you have bought all sorts of stuff from me, I should be able to build a model that is unique to you. Now, think about what that means. A&P has, which is a small chain in New York and Pennsylvania and a couple other places, has 11 million loyal customers. If I were building a model for each and every one of these guys, I have to build 11 million models. Remember the cloud of dots that I was talking about? I got to stick 11 million lines through that. Then I got to confirm, going back to this thing that we were talking about, then I got to go back over here, test everything. I have to estimate all the 11 million models. Then I have to test it. Then I have to see if I made a mistake and I have to repeat it. How many modelers in the room would attempt that? How many would like to attempt that? Well, we did that. And the really cool thing about it is that the estimation process took about 2 minutes. CPU time. So what does that mean? That means that if you screwed up, it's 2 minutes. And since you're sitting on the same copy of the data that A&P is using for their entire data warehouse operations, everything that they do off of their data warehouse, since you're sitting on the same copy, you're good. Life is good. You can basically run over and over and over again 100 times and try all sorts of different ideas and fail early and often. That's my motto. Because I figure if I fail 100 times and it only costs me a minute or two each time, by the time I get to the other end, out of those 100 failures, one of them is going to be a good idea. And I'll build those models and deliver them. So that's what we did here. We built a model specific to each brand. So we weren't happy with the million models. We wanted to build each one for every brand. So are you going to buy a Bounty paper towel the next time you walk in? What is the probability that I can assign to that one event based on your personal track record of stuff that you have bought? Can I do that? So we did. So that generates a shopping list. And that shopping list is ultimately what you're going to put in front of people. Now, that's what, think about, again, go back to the Amazon example. In the Amazon example, we were looking at the affinities, meaning that I am like everybody else in the universe when they go shopping at Amazon. There's something to be said for that, and there's lift in that, don't get me wrong. But if you're building a model on my behavior and taking advantage of the affinity alongside of it, or in fact in part and parcel of that behavior, then you can build a substantially more accurate set of models. In fact, if you took that even one step further and started to look at affinity not by itself, models not by themselves, but actually affinity as a function of time. Meaning if you looked at the affinity of the products that I buy in a single event, I walk into my local grocery store, and I buy one of these, and I buy one of those, and I buy one of these other things, and put them together, and here's my basket, and I walk away. And they look at the affinity of these products that go together in the same basket. Now, we define the basket and say, one event is not enough. I want 10 events, 100 events, 1,000 events, all events put together. And I want to look at the strength of those affinities alongside all of that product set that this person has bought. And in fact, that becomes a graph theory problem. How many people already see the graph theory problem? The graph theory problem is this, is that the strength of the relationship between every one of the products that you have in the set of all products that you bought is effectively a node, the product, another node, product, and a line that goes between them. So you got yourself a relationship between two products. You can imagine that be 100 products, 1,000 products that I bought. So now you have a graph theory problem. Because you have the link between all the products, and you have the products, the volume of each one of them is the size of the dot, and the width of the line is the number of times the strength of the affinity between those two products. But you're still just talking about me. You're not talking about me in conjunction to the rest of the world. So you've now measured the affinity of the products that I buy within my super basket, which is all the stuff that I buy. Now you incorporate that into the model. And by the way, we have yet to leave the database. We're still doing everything directly in the database. I haven't taken anything out of the platform yet. I haven't gone to SAS to do something and R to do something else, and then over here doing a little bit of C, handcrafting a little bit of data set over here. None of that. So not only are we saving time on the estimation of the models, we're also saving time on the whole moving data. How many people spend? I did this, a part of this talk I did at an event. And it was very interesting. I described that graph that I showed you, the flowchart that I showed you a minute ago. And I went through and I said, you sit there, you're in meetings, you're having political conversations over whether or not you should have access to the data, and there's all these people making decisions for you, and stuff is going back and forth, and it's really complicated. And then you finally gain access after about 6 months, a year. You get a sample of data. It's the wrong sample. You screwed up. Now you're shy. You don't want to go back. It's really a problem that you're contending with. So I made the presentation and talked about it. Afterwards, this guy came over to me and said, and he was wistful. He was like ready to cry. He said, "You just described the last 2 years of my life. Can I get a job? Coming and working. Can I get a job, please? I don't want to do that anymore." So this process that we go through of the estimation and the incorporation of all of this different sort of ways of looking at the data all in one place is really going to enable us to generate a substantially more accurate model. And by the way, this model that is getting generated is not just good for estimating what I am going to buy. It's also good because you're managing your inventory substantially more accurately. In this business case, what we did is we actually measured the number of times that they had out-of-stock conditions. When you go to a store and the product that you're interested in is not there, that is referred to as an out-of-stock condition for those of you who haven't done retail. That out-of-stock condition costs the retailer money because you're going to walk out and go down the street and buy something else. So there it is. If you can measure the out-of-stock condition, and there are ways of doing that, we measured that, and we found for this particular retailer, it was something like in the order of 5 to 7% out-of-stock conditions on these items. And lo and behold, our estimate of what the volume of demand is going to be was consistently, over a 25-month period, 5 to 7% above their actual inventory. So we estimated correctly what people were going to buy on the aggregate. So if they had that additional 5 to 7%, and by the way, we knew which store was out of stock as a result of this ahead of time. So the business implication now goes into not just a better experience for the shopper, but it goes into a better management of the store. So it's a completely sort of useful kind of thing. We, by the way, also included all sorts of other data into the exercise, which was very useful. Now, for those of you who are statisticians in the room, so I said I estimated tons of models. Millions of models were estimated as a result of this. So if you have millions of models and you have one thing that you care about, right, whether or not I'm going to buy something next time I walk in, what you want to know is that line that you stuck through, what the slope of that line is for each person. If you grab the slope of that line, and in this case what I'm looking at is if they bought in the last n days, will they buy in the next n days? That was what we were looking for in this particular variable. And the slope of that line is basically effectively the correlation between those two questions, right? If you buy more, if you bought in the last n days, are you more likely to buy in the next n days? And if the slope is upward, then that means it's a positive correlation. If it's downwards, it's a negative correlation, meaning no. If you buy more in the last 30 days, you're less likely to buy more in the next 30 days. In classical modeling, what we do is we stick one line through the cloud for this variable. And we come up with a positive or a negative correlation. And then we hang an intuition on top of it. Or sometimes we hang the intuition first, and then we go look for it. It's not clear. It's a lot of magic goes on. But the bottom line is that if you separated all the individuals out and started to look at each and every individual separately, you will find that there's actually a distribution to the betas, to the slope of those lines. There isn't a single line, and the distribution is not tight. We're going, look at this. It's going from negative 7.5 to 7.5. So it's like completely bifurcated. There are people who are driven. If they bought it in the last 30 days, they will definitely buy it in the next 30 days. And then there are people who, if they bought it in the last 30 days, they're not going to buy it in the next 30 days. And then there are people whose behavior from the last 30 days just doesn't matter. Now, when I say that, it just makes sense, right? I mean, you can imagine that some people consume this product much faster than other people, and some people just don't consume that product at all, or they buy it once, and they're done with it. They don't ever want to come back to it. So being able to model each individual separately is going to give you the ability to actually identify those guys individually. This is by far the most important thing that I can leave you with when you start to think about building segments of one. Now, segment of one is a term that has been used in marketing circles for a very, very long time. Marketers have talked about this forever. They always say segment of one this, segment of one that. But when it comes to actually talking to you as a singular segment, as an individual, they never do, because the computational load of being able to have that conversation, let alone the manpower that is necessary to do it, is enormous. So they don't do it. It's too much. All right. Then we decided, well, actually we did this one first, but pretend like we did this second. Then we decided we're going to do something else. We decided in mobile telephones, there's a lot of transactions. Right? Remember, I said the criteria for being able to apply this kind of an approach is that there needs to be a ton of observations on the individual. Whatever it is you're trying to predict, you have to have a ton of observations on it. So here's a country's worth of cell phone traffic for an entire 2-year period of time. We took all of the transactions that they had. How many people know what a CDR is? 1, 2, 3, 4. Good. CDR is basically a call detail record. It basically tells you when the call originated, where did it originate, which number, and where did it terminate, and then how long did it last, and what, if it was on a cell, which cell tower did it start on, and which cell tower did it end on, and a bunch of other things that go on with it, which have to do with the quality of service and so on. That's what a CDR is. That's an event in time. The average user of a cell phone in North America touches their phone over 100 times a day. And that does not, I firmly believe, although that's a number that has been published, I firmly believe that does not include teenagers. I think they are like way over to the right. It's 100 per minute, I think. So what is going on is that every one of those transactions is a CDR. It shows in MMS, in SMS, in websites that they go look at. It shows in the phone calls that they're going to make. All of that is collected. So now imagine all of that traffic is in one place, and you're trying to figure out what the person is going to do next. Is this person going to churn? That's one question. How are you going to figure that out? Well, if it's a teenager, then it is highly likely that if their clique of other kids leave AT&T and go to Verizon, well, so will this teenager. Boom, gone. Can you identify the clique? That's the first question. Graph theory problem. Right? I mean, it's a classical graph theory problem. What you're trying to figure out is all the begin and ends and all the relationships that exist. You're trying to figure all of them out and then create cliques. Each of these dots is a clique. This is zoomed into one piece of the graph. It's much, much bigger. But you look at one piece of the puzzle and you say, all right, I understand what's happening here. This group is self-contained. This is a K-connected network, for those of you who graph theory buffs. That's a K-connected. This one is not, but maybe this one is. That's not either. But if it's fully connected, meaning every group is connected to every other group. If every person is connected to every other person, that's a K-connected network. And you have a bunch of those. And then you have a bunch of networks where there's all sorts of weird connections. Like this one is massive. This is the middle of the bucket, right? This is massive. There are all sorts of groups of people around that are talking to each other. So you identify that, and then from those relationships, you can basically say, cool, if one of the members, which is the influencer, leaves, how likely is it that the others will leave? And you can figure out who the influencer is, and there are papers written on this, all sorts of work that has been done in this area. The influencer is the person that initiates the majority of the calls, or the person that receives the majority of the calls. You can sort of come up with your own metric as to what an influencer is. So you compute all of that, and then you estimate models for each and every person in this massive network. So if you take a city size in that country, it would be about 1.5 million people. 1.8 million to be exact on the exercise that we went through. So we built the models for each individual, trying to figure out, both because of the traffic that they exhibited and the interactions that they have with their phone, and because of the membership that they exhibited as part of these cliques, how likely they would be to leave the network. And then how likely they would be if we looked at conditional on their neighbor having left, the other members of the clique having left. And then we started to look at how much more lift we had as a result of doing this kind of a thing. And we observed that we had, in some cases, we had 30 to 40% additional accuracy in identifying who's going to leave in short term. To wrap your head around what that means, anybody work for AT&T? Anybody works for AT&T? AT&T loses some ridiculous amount of money. Their churn, according to them, is about 1% annually. According to some other observers, it's upwards of 7 or 8% churn, meaning that they lose 7 or 8% of their client base every year. So you have that much, anywhere from 1 to 8%, depending on who you believe, is leaving. You do the math. 8% of 140 million people, 1% of 140 million people, which is their user base, at about $100 a month. That's a few bucks. I'll take that for a month and retire. So what you want to do is any additional lift that you can get, even if it's like those of you who are lift chart buffs, if I can see light coming through the two lift charts, life is good. I have just improved by ridiculous amounts of money. So that's what we did here for this particular phone company, and we generated the models, and we generated the scores for them for the probability that somebody is going to default. So this was the second example of this idea of building on a segment of one. This is a problem, this is a class of problem that lends itself very well to doing that. Additionally, there was one other benefit. Because now that I know the probabilities, I also happen to know from the probabilities and from the betas, remember I showed you a distribution of the betas, from the betas I was able to figure out what the reason was that somebody was going to leave. So I know you're going to leave, and I know why you're going to leave. Now imagine you're a marketer. You know I'm about to leave, you know the reason, you're going to have a different conversation with me than somebody else who's going to leave for a different reason. I care about the device. I want the coolest, the 5S, not the 5. If you give me the 5, you know, I'm not hip anymore. And if you give me the 5S, I'm all, you know, with it and up to date. So I want that. So talk to me about that. Whereas with somebody else, it might be that the plan is way too expensive for me. I'm shopping. And I want to figure out how to buy something cheaper, a cheaper service. So we generate that and we hand it over, and marketers are all happy about that. Switch gears. So if this works in these areas, why wouldn't it work in econometrics? So this is, I spent 12 years of my life doing this, so I said, why am I doing stuff that I haven't spent enough time doing? Let me go back to something that I know a little bit more about. So here what we were worried about is being able to predict when somebody is going to prepay their mortgage. Interest rates fall. I borrowed at 7%. Now interest rates are at 4%. Maybe I should refinance. And if I refinance, the guy who invested in me to borrow money so I can buy the house, he's out cash flow. He wants to know. Well, the hedge fund, there's a whole food chain. And if anybody's interested in that food chain and wants to talk about it, let me know. We'll talk about that as well. But you want to identify that individual that is going to do that as granularly as possible. Now here's a counterexample to some of the other stuff that I was telling you about before. In the telephone example, I have thousands, tens of thousands, hundreds of thousands of transactions potentially. In the case of retail, once a week, twice a week, somebody goes and makes a purchase. Sometimes there's 2 or 3 purchases a day that occur. So I go visit and I forget this thing that my wife told me, and I'm paying attention, and I'm in trouble, so I turn around and go back and grab that thing and go. That kind of thing means multiple transactions, so they have every one of those as a touch point, and you've collected all of that. And if it's a household, if it's properly householded, that could be, 10 transactions a month, 15 transactions a month. When it gets to house payments, mortgage payments, it's once a month, maybe twice a month. That's not enough. There isn't enough stuff going on with one person anymore. So now the unit of analysis is going to change from an individual person. By the way, I have the data on each individual mortgage in the US. All 57 million of them that are outstanding today, I monitor them on a regular basis. Every month, everything that happens to them comes to us. We collect and make it available to our clients. So I look at that all the time. So what's going on? There's a whole bunch of drivers that are going on here. There's unemployment, house prices, interest rate, blah, blah, blah. Plus I have the activities of the loan itself. So I take all of that information, put it together, but this time I'm forced to group loans together. I can't do it as well as I did before. I'm forced to do that. So I have to give up, and instead of building 1,600 models, 1,600 different types of products, we actually built 25,000 of them. So that was a cop-out. Anybody ever built 25,000 models? It was a cop-out because we didn't have enough data. So the data basically dictated that we had to do it a different way. So we did. We built separate models. And then what we did is we tried to deal with this problem. So if you're not steeped in econometrics, some of this terminology may seem a little weird, but this is what is referred to as idiosyncratic risk. In other words, I have no clue why this is happening. So I'm just going to call it idiosyncratic. That's the definition. There's a lot of literature, people argue about it, and then it doesn't matter. It just means they don't know. So when they don't know and the model just doesn't fit properly, they call it idiosyncratic risk. They say, well, it fits in all these other cases. This is the only one that it doesn't fit, so it must be idiosyncratic. Well, I wanted to take that on, and I wanted to generate more accurate predictions of prepayment behavior on every one of the loans that I was analyzing. So we did. Now, these other drivers of behavior, of the prepayment behavior, are classical. Again, if you go to literature, you'll see every single one of those as the driver of the behavior. So very common to use that. So what we did is we built those models. Now, when you build a model, what you're doing in every case that I've talked about, all the models that I've talked about so far, this is exactly what we generate. We generate a lift chart. And you can take that lift chart and you can summarize it into something called the area under the curve. And if you want to know what that means, it's basically a ratio of this area to this full area, between the distance between the red and the blue versus the green and the blue. So that ratio is area under the curve. The closer to 1 it is, the better your model. The closer to this line you become, the more problems you have. If you're very close to 1, you're lying because something is going on. You're right on top of perfection. You either have a wizard hat or something else is going on. So this chart that you're seeing is an example of a very good model. So if I'm over here, something funny is going on. You know, if the AUC that I'm generating is closer to 1, something funny is going on. I have some autocorrelated variable in the model. If I'm way down here, I need to worry maybe I'm not modeling it correctly. Maybe I don't have all this stuff in there. If I normally build a model, what I'm doing is I'm generating an AUC, a single number. I build one model across the board. Now that's not entirely fair because on Wall Street they build families of models for this kind of a problem. They build something in the order of about 10 or 15 of them. That's a classical way that you do it. That means 10 or 15 dots are going to appear here. What I'm showing you is a continuum. For the thousands of models that were built, or the tens of thousands of models that were built, I have a distribution. And that distribution is telling you something. Now, that distribution is saying that the low end, there are some models that I built that are junk. They're just bad models. So out of the 25,000, there's a whole bunch of models that actually extend beyond the 0.05 to 1. There's a whole bunch of them over here that I haven't shown in this graph. And those are the bad models that I ended up building. And then these are the models that have some sort of distribution to them in terms of the quality of the model. So if you're more familiar with KS statistics, imagine this is a distribution of KS statistics. Not much difference between them. What you're seeing is instead of having one dot somewhere typically here or here, I have a whole distribution. I can rely on these models substantially more than I can rely on these models. And I am not catering to the middle anymore. I'm not driven by the middle, and I make less assumptions about the distribution of the data that is coming in. That's a much stronger foundation for building models. And then what happens is if you want to do, you build all your models, you want to actually generate something as a result of those models. You want to figure out what the cash flow is going to look like. Well, you have to do a Monte Carlo simulation for some of those variables that I was showing you earlier. You have to go, You have to go and take interest rates and house prices, and you have to do a Monte Carlo simulation of the different values that those can have over the course of time, because a mortgage is a financial relationship that you're going to hold for 30 years. So I have to figure out what's going to happen in the next 30 years to interest rates. I have to figure it out for house prices. And just generate a Monte Carlo simulation very wide, and then figure out what my cash flow is going to look like at every one of those points. Well, what happens using those, if I built only a handful of models, 10 or so models, this is, the red is where the intensity of the payoff is very high, meaning the cash flow is very, very fast, meaning that the investor is losing a lot of money. It's all concentrated down here, meaning that under different interest rate scenarios, this guy is not going to lose money. Under other cases, things are very, very stable, and this is a lot of money lost. And a lot of the money is getting lost very, very early in the process. This is if you only have 10 models. Now go back to what happened in 2007, 2008. The majority of Wall Street was doing this. They were looking at these Monte Carlo simulations. They looked at the distribution of the results out of the Monte Carlo simulation, and they came up with this kind of a thing. They said, oh, this is a very unusual event out here for house prices and for interest rates. So I'm not going to worry about it. That's not an unusual event. And in fact, if you start to look at it more holistically, meaning that you're building models that are very, very unique to each individual collection of mortgages, what you're going to find is that there's actually waves of prepayment that are going to take place under different scenarios. In other words, your risk is substantially higher on your overall portfolio and overall collateral that you're holding. It's a much riskier thing that's going on, in other words. So our models, in contrast to what this was doing, basically said that you have a set of waves of risk that are coming at you. And prepayment is going to occur, and by the time you get to this point in the process, then a lot of, granted the higher risks are down here, but you definitely still have some risk even in the unusual cases, which is the unusual cases that happened to house prices in 2007, 2006, 2008, like that whole thing. And then you had the credit crunch to sort of screw everything up doubly so. So again, another case made for the idea of finding the right problem and building the right class of models for them. Now, if all of this took an insane amount of time to do, we would never do it. I did this with Zero Sleep, me and another person in my team, over the course of 2 weeks. Contrast that to what happens on Wall Street. Wall Street, you're 2 years with a team, massive team, and they don't sleep either. I was there. So that's what happens. The speed becomes a real integral part of the exploration of all this stuff. And that's sort of what we do, at the core of what 1010 does is that speed, and that sort of allows us to do these kinds of wild experiments. So what we do is we have all of this in-database technology and all the capabilities that I was talking about. So I talked about graph theory. I talked about modeling. I talked about reporting. I showed you a visualization and some example code. I talked about sort of a Monte Carlo simulation and bringing all of this together in one place. There aren't other, if you're talking about ridiculously large volumes of data, it becomes really, really difficult to do that all in one place. You usually have to move data around to do one, and then move it again to do something else, and so on. And oh, by the way, to do all of this, I had to do ETL, and I had to do all sorts of other things. So all of that is occurring inside of the same platform. And then if I have something that if I have an idea that I don't have currently in the platform, I have to implement it in the query language that I was talking about. So the expressive power of the query language that you have is paramount to your success. So one of the things I had to do is build an autoregressive model. And at the time, I didn't have an AR or an arch. So I needed to write that in the query language. One of the guys on my team wrote it. This is the entire code base for an autoregressive. And if you really want to see exactly what he's doing, you can come up and look at it up close. But that's it, 10 lines. Implementation of an interesting algorithm in 10 lines is sort of tough. So the language that you're using to do this has to support it. So all the stuff that I was talking about graph theory and Monte Carlo simulation and reporting, standard reporting, killing the data warehouse, all of that stuff has to happen in a single place on a single copy of the data. Otherwise, the scheme that I'm describing ain't going to work. With that, I'll stop. Any questions? Yes?
I do have a question. With so many models being formulated, how do you manage overfitting and testing of all those models and multiple comparisons, corrections, that whole soup of things?
It's a royal pain. No two ways about it. But remember, if I'm able to, if I'm able to measure something, some statistical property of the model that I just generated, you were talking about overfit. So if I'm measuring something about overfit, and different people have different religion about how to measure overfit. But if I'm measuring it, whatever the methodology is, and I'm measuring it on 1 million models, that in and of itself is a lot of data. So now I have to look at distributions of those and start to apply statistics to that to try to find anomalous behavior, things that I don't like, things that I do like. So some of that is going to end up being in the category of art and less science. Because frankly, I've looked high and low in the literature to see if anybody else is foolish enough to do this, and the answer is no. Nobody else has done this. So people don't know the properties of groups of models. They know properties of individual models, and they try to understand that. And we're trying to apply that kind of an understanding back to millions of models. But it's a challenge.
So you can't think in terms of like false discovery rate because these are not independent observations. Is that kind of
you can, but you're imagine each model as an independent, is a separate model. Imagine that being a separate model. The simplest version of it is the autoregressive one, where you're looking to see what the volume of something is going to be going forward. And if you're doing that on a single line, then you can generate the autoregressive stuff, and it's fairly simple to test it if it was one line. If you have 1,000 of them, 1 million of them, then you measure the same thing 1 million times, and then you look to see if the distribution suggests something weird to you. So we do that. The other thing is, I don't like distribution of data as being very wide. So when I generate the betas for all the different models that are there, if I see that the beta distribution is very, very wide, I get nervous.
So that's suggesting this class of models is high variance.
Correct.
Subject to being
so the high variance problem is, so classically what you want in modeling is you want to have some variance in the data that is being observed. If you have 0 variance, there's really little to be done. So you want some variance in the data. If the variance is occurring within the population that you're building your models on, meaning that all of my phone calls, and you're looking at that, and hopefully there's a little bit of variance, otherwise there's nothing to be said, other than just straight lining it. But to go back to your point, if there's very little variance, then you have to start to look at groups of observations, the same way that I did with mortgages. Because within a mortgage, there is variance, meaning that I have delinquencies. And those delinquencies are predictor of behavior. And I can also say, this month I'm going to pay an extra $100. My lottery ticket won an extra $50, so there it is. So that kind of thing can happen, and you can use that as your variance. The problem is that that's not enough. And the overwhelming majority of the loans that are outstanding are current, and people are paying their mortgages on time, and they're not introducing any variance. So what you want is you want to group things together so that there is some variance, but not so much that it becomes another issue. But we have the same problem post-modeling. You've generated 1 million models that in and of itself, it's not by the way, I only said big data once. Just want to make that point. Because, we're dealing with a ton of data. And in fact, in the models that I'm building, that in and of itself becomes a big amount of data. So
neither neither is in.
Exactly. It is a problem. So you're absolutely right. That piece of the puzzle is not a well-developed science, but we're finding that the classical intuitions are applicable, and we're deploying them, and we're finding very, very good results with the models that we're generating. Yes?
Can you talk a little bit about the stack that you guys use? Is it fully custom, or is it based on top of some sort of relational database? Would be like my first slide.
There is no stack.
Right. You just have one.
It's just one thing.
One database.
Everything is one thing.
But is it custom built?
Everything from scratch, every line of code is Fentek. Every line of code is us. So, and everything is basically, the entire thing is the stack. Meaning, everything from from floor space, electricity, air conditioning, operating system, hardware, database, the BI tool, the visualization, the modeling tool, the querying tool, all of them live on a single plane, completely flat, except for the operating system and the hardware. I haven't figured out how to get rid of that yet. But the rest of it is all us. Everything is us, and we're sort of doing everything in one shot. Yes?
So you said that the data has to be time series with lots of records. What do you do if there's like a new SKU or a new customer?
Not a problem. A time series can have one observation. It's sort of a bummer, and I can't actually build a model on that. A brand new SKU happens all the time. In fact, if you look at, so in classical data warehousing, they would call that a slow-moving dimension. So a slow-moving dimension is when you slowly add new items to a dimension in a star or a star schema. Since we don't have schemas, by the way, so if you're wondering, schema-free, no SQL. So if you start to think about it in those terms, what you have is a different, so yes, there are cases where I can't build a model, and that's if there's only one observation. I can store it, and I can hope there will be a little bit more and a little bit longer. If the SKU is brand new, it will get added into the table that I have, and when it has enough observations, I can do something with it. But in the meantime, I wait. Yes?
So how do you handle missing data, or do you have missing data?
Of course you have missing data. Retail is notoriously dirty, just insanely dirty. Finance is a little bit cleaner. So mortgages are pretty clean. When you look at sort of what's happening, not because servicers are very good at sort of reporting their data, but because all the folks that are in between the servicers and us, those guys clean the data as a company. But then we also have our own ETL process that we go through. Missing data, so there are a bunch of problems. When the data comes in on day one, and your application is a data warehouse application, like Rite Aid and Dollar General are for two of our clients where they use us as a data warehouse. In those cases, I can't touch the data because they want to know, warts and all, they want to know what's going on. So for that purpose, I can't really touch it. But I can put business rules on top of that that says, oh, if the following three conditions occur, this is how you should interpret this stuff. And then I have a query that does that, package that query up and slap a pretty face on it, and put it back in front of the client. So we do that as a means of dealing with it. The other piece of it is the ETL on the way in. So there are cases where we clean the data as early as possible. I hate that. And I keep telling the guys that do that to cut it out. Because I'll give you one example. I used to work for Equifax. Equifax, everybody knows who Equifax is. Your credit reports come through them. So your credit history lives with them. I have all of the credit history for the whole US on the 1010 platform. So one of the things that they do is they monitor your credit card. And if you're delinquent on your credit card, the servicer reports that. They say Afshin has been delinquent to the tune of 5 days. Well, 5 days, Equifax doesn't really care about it, plus they don't want to save an integer. So what they do is they want to save the Boolean, and the Boolean is basically 30, 60, 90. So you have 30, yes, no, 60, yes, no, 90, yes, no. That's what they want to save. So what they did instead is they threw the 5 days on the ground as part of the ETL process, and they waited until I was 30 days delinquent to say that I was 30 days delinquent, which is insane. I was 5 days delinquent or 7 days, and that's information. There is signal in that. It says something about my stability as a borrower. And you threw that data on the floor. Shame on you. So for me to go back and get that data, I had to crawl back down through the stack, go all the way to this mess, and then find out where that data was being reported, and then try to recapture it. When I asked for that, I was laughed out of the room. Because they said, do you realize that that's like a $10 million request you're making? For me to change my ETL code to be able to do that, which is written in Assembler 370, are you out of your mind? So that's what I was told. I stopped asking for it. But so that's why I hate it. I hate it when people transform the data, a priority of the analyst, of the business analyst, of the modeler, of that guy who is connected to the real question. When they make that decision, which is an IT decision typically, somebody decides that it's more efficient to save binary rather than integer, I just don't like that guy. Because he limits my ability to ask cool questions. Yes?
So you talk about the grocery, the ANP example. You talk about like correlation between the past period and next period. You guys use like different time window to see, certain product have a different like.
Absolutely. So the speed, the velocity they call it in retail, the velocity of purchase is different depending on which product you're looking at. So some products are, so Bounty, if I remember, I may not have the exact number, but it was in the order of 180 days. Is sort of the speed, the velocity, right? There are other products, like bananas, are weekly. Bananas are basically bought every time. Catch yourself. Next time you go to the store, I promise you the probability that you will buy bananas is extremely high. Just true. So the velocity is very, very high for bananas. For Bounty, paper towel, upwards of 100 plus days, 180 days. So you have to take that into account. Yes?
Well, not this last question, but the question right before that, you mentioned two types of data, pre-formatted data and unformatted 40 raw data. Mm-hmm. So are you suggesting that your query language each time will do the transformation to turn it into something useful? So as you've got it stored, every time you're having to do that transformation?
If the speed with which I can do the transformation is infinitesimally small. I remember a long time ago when I was doing my graduate work, somebody said, imagine the computer as small as a pin, and as red as you can possibly imagine it, running really, really hot, and ridiculously fast. So small and ridiculously fast. If I can do that, then why does it matter if the ETL is happening day one or at the absolute last moment? It doesn't matter. So if I can query the database, and if I can estimate 1 million models in 2 minutes, or if I can generate, if I can plow through 57 billion rows of data in 10 seconds, it doesn't matter.
But doesn't that necessitate that the language itself hides a lot of details under the hood?
Which details?
Well, in particular, how you're actually processing the data or doing that parsing.
So there is a problem with the approach that I'm advocating. I'll tell you what the problem is. I don't think that's the problem that we have. The problem is somewhere else. The problem is that the business rules that govern the way that you should interpret the data are now getting executed with every query. And that can get confusing if I give the control of that to the guy who manages the meat section, and the guy who manages the produce section, and the guy who sells beer. And like, each one of those is going to want to sort of tweak this stuff and mess with it. Well, we control that. And the way that we control that is we give a set of reports to the operational people that they don't have choices in. So we hide that flexibility, but you can't not do that. Otherwise, there would be inconsistent conversation. On the other hand, for the guy who's actually the analyst who's asking the new questions, the cool questions, the interesting stuff, that guy wants to have free reign of the data. So that guy should have the option to actually ask anything they want to ask on the raw, dirty, disgusting data that comes in. That's sort of the balance that you have to play with. There are cases. We are, for example, I won't mention their name. They're very big, and their data is really disgusting. Like, really bad. And the reason is they bought a whole bunch of little companies. And every time they bought a little company, they brought the data in, and it looks different, it feels different, the decimal points are used or not used, interest rates are 1.2%, or it is divided by 100, and they put it in there. It's a mess. But you have all of that data, and you have to enable people to do the analysis, both on the messy stuff and on the cleaned up version. So in those cases, we actually go through an ETL process and create a standardized version of this stuff. So now we have 2 copies. And that's where I get a little, keep the original, whatever you do. Just don't throw the original away. And give access to the analyst who wants to ask the really cool questions. There was a question on this side. I think they gave up. Any other questions? Well, I really thank you for your attention. Have a great day.
Thank you, everyone. And if there are pizza boxes left, you can probably take one. That's the biggest sort of thing to take. Yes.
Yeah.